Hello, students, and welcome. Today, we're going to tackle a very important topic from our first unit, electric charges and fields. We'll be talking about electric flux. Now, I know that name might sound a little bit complicated, but I promise you, by the end of this session, you'll understand it so well, you'll never forget it. And, most importantly, we'll learn it in a way that helps you score full marks in your exams. So let's begin. Okay, before we even look at a single physics formula, let's start with a really simple question. Just imagine it's raining outside. You have a bucket, and you want to collect as much rainwater as you can. Tell me, how would you hold the bucket? Simple, isn't it? You would hold the bucket straight, with its mouth facing the sky, completely horizontal. Why? Because this way, the entire opening is facing the rain, and you catch the absolute maximum amount of water. Obvious, right? Now, what if you start tilting the bucket? You can just imagine it. Less water will go in. The bucket's opening is the same size, of course, but because it's at an angle, the effective area that's facing the rain has become smaller. So, naturally, you catch less water. And believe it or not, this simple idea is the entire concept of electric flux. In physics, just replace the raindrops with invisible electric field lines. And instead of a bucket opening, we have some kind of surface area. So, the amount of water we caught? That is just like electric flux. It's nothing more than a way to count how many electric field lines are passing through a surface. That's it. So, let's get a bit more formal now. What is electric flux? At its heart, it's simply a way to measure, or, to count, the number of electric field lines that are passing through a given area. Now, for your exams, the exact NCRT definition is very important. Let's look at the slide. Electric flux, which we write as delta phi, through a small area element, delta S, is defined by the formula delta phi equals E dot delta S. Remember your dot products from vectors? This expands to E times delta S times cos theta. And this whole value is proportional to the number of field lines cutting that area. Okay, let's break that formula down, because this is where the confusion starts. E is just the strength of the electric field. Delta S is the size of our area. But the most important part, the real hero of this formula, is the angle theta. Now please, look at the diagram very carefully. We treat the area as a vector, and its direction is given by the normal. That's a line we draw perpendicular at 90 degrees to the surface. So theta is not the angle between the field and the surface itself. No, it is the angle between the electric field vector E and the normal to the surface. Please remember this. So you see, that formula, E delta S cos theta, tells us a very clear story. The electric flux really just depends on three simple things. Let's break them down one by one. First, the field strength, E. If you have a stronger field, the field lines are packed closer together. They're more dense. So for the same area, more lines are going to pass through. More E means more flux. Simple. Second, the area, delta S. This is just our bucket example. A bigger bucket opening catches more rain. A larger area will catch more field lines. More S means more flux. And finally, the angle, theta, through cos theta. This is our tilting factor. It tells us how well the area is lined up with the field. All right, enough theory. Let's make this crystal clear with a super simple numerical problem. Imagine we have a uniform electric field of 10 newtons per coulomb, and it's passing perpendicular to a flat surface that has an area of 2 square meters. The question is, what's the electric flux? Let's solve this step by step, just like in an exam. We are given E is 10, A is 2. Now the angle. The question says the field is perpendicular to the surface. Now think, if the field lines are hitting the surface at 90 degrees, what is their direction relative to the normal? They are going in the same direction as the normal. They are parallel to the normal. So the angle theta between E and the normal is 0 degrees. See? That's the trick. Now just plug it in. Flux is E times A times cos theta. That's 10 into 2 into cos of 0. And cos of 0 is 1. So the flux is just 20. The units are Newton meter squared per coulomb. Easy, right? Okay, now for a really important section. Let's talk about the small mistakes that can make you lose marks in your exam. I like to call them silent killers because they look small, but they can give you a completely wrong answer. So please listen very carefully. Mistake number 1. Students sometimes think flux is a vector. It is not. Remember, flux comes from a dot product, E dot delta S. A dot product always gives a scalar. Flux is just a number. It tells you how many lines are passing through. It doesn't have any direction. The second mistake, and this is the most common one, is using the wrong angle. Many students take the angle between the E field and the surface itself. That is wrong. I'm saying this for the third time. The angle theta is always between the electric field vector and the normal to the surface. So you might be wondering, sir, why are we spending so much time learning to count these imaginary lines? Does it actually matter? And the answer is a huge yes. This concept isn't just some small topic. It is the fundamental key that unlocks one of the most powerful and beautiful laws in all of electricity. And that law is Gauss's law. You see, you cannot understand Gauss's law without first understanding electric flux. Electric flux is the language that Gauss's law speaks. So what we have learned today is the essential foundation, the first step for our next very important topic. All right, so let's quickly summarize everything for your notes. Point 1. Electric flux is simply a count of the number of electric field lines passing through a surface. Point 2. It's a scalar quantity, not a vector. Point 3. It depends on three things: the field E, the area S, and the angle theta. Point 4, and the most important one, the angle theta is always between the electric field and the normal to the area. And finally, the SI unit is Newton meter squared per coulomb. To finish up, let me leave you with a question to think about. We now know how to count field lines passing through an open surface, like a sheet of paper. But what happens if the surface is completely closed? You know, like a box or a football. What would be the total net flux passing through the entire closed surface? Think about that, because that question leads us directly to Gauss's law. We'll explore that in our next session. Thank you.